Okay, so I guess last I didn't discuss the complete proof of Taylor's theorem clearly. So let me do it once more. And since many of you were absent also. So the statement of the theorem was we defined the Taylor's polynomial Pn. So Pn of x is so first we have a function for any um, n times or n plus 1 times differentiable functions f from open interval ab to r. It's n plus 1 times differentiable on this interval. So all the first derivatives, second derivatives, third derivatives up till fn plus 1 are defined on this interval. So now uh, for all points c in open interval ab, we are defining this Taylor polynomial as as p n x equals fc plus f dash c times x minus c plus 1 by 2 factorial f double dash c times x minus c squared and up till 1 by n factorial times f n derivative of f minus c power n. So it can be compactly written as irons from 0 through n. Sorry. FIC times I factorial times x minus c power I. Yeah, okay. Where the zeroth derivative is defined as f itself. Okay, so now we want to use, we claim this polynomial p and x is a very good approximation to the function fx. And the Taylor's theorem. So the Taylor's theorem says that given a Taylor polynomial and a function fx, we have fx equals to pnx plus rnx. And Rn is the error quantity. And Rn is given by, so we have an interval AB, which is the domain of f, where f is n plus 1 times differentiable. And we also have a point C around which we are calculating the Taylor polynomial Pnx. So C is also in that open interval AB. And this approximation, this variable x has to lie inside AB. Okay, so x also has to be inside AB. And now if either C is less than x or this, sorry, or C is greater than x. So in this case, there exists some, uh, let me say zeta in Cx, and in this case there exists some zeta in Xc, such that Rnx is defined to be equal to, don't have space here, such that Rnx is Fn plus 1 So this is the error quantity. So basically, the error term is just the n plus 1th term of this polynomial, but evaluated at a different point, not at C. It's evaluated at a point zeta, which is in open interval Cx or Xc. So there exists such a point zeta where the error exactly matches, which error is exactly the original error in the approximation. Okay, so now the proof. Just a minute. Okay, so now let us define an error function gx. So what is an error function? It is the difference between uh, the function, the original value of the function fx, and our approximation pnx. And expanding it, you will get something like, or sorry, actually the variables are. Okay, so now we are fixing the values of c and x. Okay, so fix c and x inside the open interval of our domain. And now for all t in AB, t is another variable. We are defining gt as ft minus pnt. That is equal to sorry, not ft, fx. So we are varying c. So fx minus, this is not pnt, sorry. So the expression of pn takes three things, you can say. One is, so pn depends on three things. One is n, one in x, and other is c. So we are only varying the third quantity c. So fx minus ft, since it was fc last in the original pn expression, then x minus t minus 1 by 2 factorial, and so on up till n. So now observe that gx, so what is gx? This is a constant. Ft is fx, so this cancels, and then all the rest of the terms, since all of them have a factor x minus t, they evaluate at x is equals to 0. So gx is 0. And what is the value of g dashed? I mean, what is the expression for g dash t? So this one is a constant. This goes to 0. This is f dash t. And this is minus s f double dashed t times x minus t plus, sorry, not plus, minus f dashed t times, sorry, yeah, plus f dash t, since the derivative of x minus t is minus 1 and multiplied with f dash t is plus f dash t. Similarly, we have minus 1 by 2 factorial f triple dashed sorry, I shouldn't write it here. Triple dash t times x minus t squared and plus f double dashed t times x minus t. Since the 2 got cancelled with the 2 factorial and the minus made it plus. So now you can see we are in a telescope formation. So this get cancelled out. This will again get cancelled out and like that, so on. So we will be left with the last term only, right? So the derivative of the last term will be 1 by n factorial times f n plus 1 t times x minus t power n and plus 1 by n factorial f n t times x minus t power n minus 1. That's it, yeah. Just a minute. There will be an n here. So this is basically n minus 1 factorial. So this term, this will get cancelled, right? This will get cancelled and we will be left with only this term. So therefore g dashed t is, this is minus, right? So minus 1 by n factorial f power n plus 1, n plus 1 derivative of f at t times x minus t power n. So there, so here we have the expressions for g dash t and gx is 0. Now we define another function hc or ht. I mean, t is a variable, c and x are constant. So ht is gt minus x minus t by x minus c power n plus 1 times gc. So what was the motivation behind this weird construction? We are basically preparing a function to apply Rolle's theorem. Okay. So we want h to be 0 at both the endpoints. The endpoints are x and c. Okay. So what is the value of h at x? So hx is gx minus the numerator goes to 0. So the whole thing goes to 0. And since we proved gx is 0, so gx is 0. So hx is 0. And what is the value of h at hc? So hc is gc minus x minus c by x minus c power n plus 1 gc. So that too is 0. Hence by Rolle's theorem. And why is h differentiable in this interval x to c? So GT is a polynomial from our definition, and polynomials are differentiable. And this is a constant term times a differentiable function, right? A mixture of polynomials and exponentials. Since hx in ht is differentiable, the interval x to c. This x to c interval may be c to x. It all depends on whether c is less than x or c is greater than or equal to x. Doesn't matter. Let c equals hx equals 0. So therefore, by Rolle's theorem, there exists a zeta inside xc such that h zeta is 0. So, h dash zeta is 0. This implies h dash zeta equals g dashed t minus, so the derivative of this one is n plus 1 times x minus t, that is a variable. So the denominator gets copied out, x minus t power n plus 1, so n plus 1 times x minus t power n. And gc is a constant. So this is 0. This implies g dashed t equals n minus, so n plus 1 by x minus c power n plus 1 times x minus t power n times gc. And g dash t, the expression for g dash t is this one. So just a minute. Did I miss somewhere? Sign shouldn't come minus actually. Oh, okay. So it was when I was differentiating it, this was x minus t, right? So the derivative will be minus 1 times that whole thing. So this would be plus. Sorry. So then here we have a minus. Here we have that minus which get cancelled with this one. Now this implies gc equals 2, so the x minus t power n gets cancelled on both sides. Oh, this was n, sorry. Handwriting is so bad. Transform into an x. So this n plus 1 and n factorial gives n plus 1 factorial times n plus 1 derivative of f at t divided by x minus c power n plus 1. So that is the value of gc, and by definition, what is the expression for gc? So gc is, I guess, fx minus pc. I mean pnx. Okay. So gc equals to fx minus pnx. This equals to So if x equals to, just a minute. Oh, sorry, why am I writing it in the denominator? So it was x. So that proves our Taylor's theorem. So the error term is indeed the nth term of the Taylor polynomial, n plus 1th term of the Taylor polynomial evaluated at, oh sorry, I should have written, what do you say, zeta in all these places, since h of zeta, I was writing h of zeta. Now it's okay, I guess. So we have proved the existence of zeta. Now we can use the Taylor's theorem and use the Taylor's polynomial as a good approximation for fx and find limits and derivatives and all that. So let's solve some problems. So the first question is evaluate x tends to 0, 1 minus cos x by x squared equals to half. Anyone has any doubts regarding the proof of this Taylor's theorem? Or is it okay? If it's okay, then how should we approach this one? How to find the limits? So of course we will use the Taylor's expansion of cos x. So cos x is infinitely differentiable function on the whole of real line. So cos x is, we call such functions smooth actually, is smooth over R, which is more than sufficient condition for applying Taylor's theorem. since x is tending towards 0, we will use the Taylor's approximation at 0. So to find Pn x at 0, so what is the derivative of, first of all we have cos c is equals to 0, and let fx equals to cos x. Therefore f0 is 0, f dashed 0 is, sorry, so sorry, f dash 0 is minus sine x, which is 0 at 0. F double dashed 0 is again minus cos x, so it's minus minus 1. F dot triple dashed 0 is again 0. F both or F40 is again, so it was minus, so it's again plus, it's plus, and so on. So all the odd derivatives evaluate to 0, and the even derivatives change signs alternatively. Therefore Pnx is 1 minus plus and so on up till the, then let me make it 2n, or let me make it 4n, doesn't matter. The 4n terms are easily positive, right? We can observe that, so it should be plus 1 by 4n factorial x power 4n, x power 4n, and then the let me make it 4n minus 1. Alright, for this problem I just need up till the third approximation, I guess. Just don't need them. So P3x is 1 minus 1 by 2, 4 factorial. So while Taylor's theorem, there exists neta inside so let's say minus 1 to, it's approximation around 0. Okay, let's say 0 to x, such that fx equals this function, that is 1 minus 1 by 2 is approximation in. What's the fourth derivative of fx? So fourth is plus 1, that is cos x. So cos eta times x power 4. Okay. So therefore now we can say fx is obviously cos x. So cos x minus 1 1 minus cos x by x squared is our expression. So let's bring the cos x onto the right side. So 1 minus cos x, and then the left hand side equals 0. So dividing by x square, we get this implies 1 minus cos x by x squared minus half. Mod of this is less than or equal to x squared by 4 factorial cos theta, since in this interval that is very close to 0, cos theta is always positive. So since cos is between 0 and 1, we can evaluate, we can find a upper bound. The upper bound is obviously x squared by 4 factorial. 4 factorial is just a constant, right? So what is x? And since x is inside, it's very close to 0, right? So we can say, like, we can take x to be inside 0 to say half, which is less than, therefore x is less than 1. Therefore x is squared, limit n tends to infinity. Sorry. I mean, just we don't need them. We just take limits on both sides. So limit x tends to 0. 1 minus cos x by x squared minus half. It's less than or equals to limit x squared by 4 factorial. Less than or equals to 0. Since this is the absolute value, it has to be 0. So this thing goes to 0. Now,
Sir, could you please scroll up a bit?
yeah.
Yes, sir, done.
Okay, so last day I was talking about Stirling's approximation, and I said we will discuss it in the next class. So then this is the next class. So Stirling's approximation. So n factorial for really large n can be approximated as 2 pi times e power minus n times n power n plus 1 by 2. The Stirling's theorem actually states a limit. It states that the limit n tends to infinity, the ratio of n factorial and 2 pi e power minus n power n plus 1 by 2 is equal to 1. So to prove this, so we will first prove a set of claims, and then one by one, and then we will use all of them to prove this Stirling's theorem. So Let's start one by one. Claim 1 is claim 1 is suppose we have a sequence xn such that sum over 1 through infinity xn plus 1 minus xn mod of the difference converges to some limit to something less than infinity. This implies limit n tends to infinity xn exists or is less than infinity. Proof is pretty simple. So what is the sum? So sum over n equals to 1 through infinity xn plus 1 minus n is equals to limit capital N tends to infinity. Sum over n equals to 1 through capital N mod of xn plus 1 minus xn. So this is equals to limit n tends to infinity. This can be expanded as so the modulus can make our life difficult. So suppose this is some kind of bifurcation. So I'm putting it inside the green box. So n tends to infinity if xn converges. This implies, or actually, if mod of xn converges, this implies limit n tends to infinity, xn converges. Why is this true? Suppose this limit is L1. So then we know there exists capital N after which mod of L1 minus xn is less than epsilon for a fixed epsilon. Sorry, mod epsilon, mod xn. And uh, and mod of xn is greater than or equals to xn. What does this imply? It implies mod of L1 so this implies mod of xn minus L1 is less than epsilon, and this implies we can replace mod of xn by xn since it's things that is much smaller than mod of x1, and this implies this one. Okay, so this is actually called, if xn is a sequence, we call the sequence mod of xn. If mod of xn converges, we say xn converges absolutely. So this is also called xn converges absolutely. So this condition implies xn converges absolutely, and absolute convergence always implies simple convergence, but the other way around, is not true always, not necessarily true. Yeah, so sorry, I mean said the reverse way around, I guess. So sorry. So absolute convergence doesn't imply total convergence, but total convergence implies absolute convergence. Sorry for that. So enough to show this mod. I'm removing it and making it just xn plus 1 minus xn. That this thing converges implies xn converges. So now we can apply the telescope. So the first term is x2 minus x1, then x3 minus x2. So it cancels out nicely. We are left with xn plus 1, I guess, minus x1. So this is limit n tends to infinity. This is capital N plus 1. Xn plus 1 minus x1. Therefore, by the problem, limit n tends to infinity, this thing exists, right? And x1 is finite, so it it doesn't depend on n. So minus x1. So this is outside the limit. The x1 is outside the limit, is less than infinity, which implies this is less than infinity. Right, so we are done, right? This n plus 1, we can just make it n by shifting the variables. Therefore, limit n tends to infinity. Xn converges. So our first claim is proved. Now claim 2. So now we will use the Taylor's theorem to show that mod of, so x is inside open interval 0, 1. Show that mod of ln of 1 plus x minus x plus x squared by 2 is less than or equal to x cubed by 3. So the proof is So we know or we can just calculate the Taylor's expansion of 1 plus log of 1 plus x, which is x minus x squared by 2 plus x cubed by 3 factorial 1 plus zeta. Zeta is that so by Taylor's theorem, there exists zeta inside if we fix x in 0, 1, so 0x, such that this happens. So this part is the P2x, or the second order approximation of ln x plus 1, and this one is the error term r2x. So adding them, we get the exact value of log of 1 plus x at that particular value of x. Okay, this is not a variable. Like this zeta actually depends on x, right? So you can write it as zeta x to remember that zeta is not independent of x. And now since zeta of x is inside 0, 1, zeta of x is less than 1, implies 1, 2 by 1 plus zeta of x, or zeta power 3 is actually less than 1. Just a minute. Can we say that? So taking them on the left hand side, so mod of this thing is, the right hand side is always already positive, so don't need to take a mod. Since this thing is less than 1, we have ln 1 plus x minus x plus x squared by 2 less than x cubed by 3 factorial. This proves the second claim also. The second claim is proved. So now we will try to prove the original limit, but without the constant term. So we will try to show limit n tends to infinity n factorial e power minus n power n plus 1 by 2. This thing exists. Observe that the original Taylor's theorem also had a root over 2 pi. That we will prove later that this thing equals, this limit is actually square root of 2 pi. So first let's prove this exists. So we will first take log. So let us define xn as ln of n factorial by e power minus n times n power n plus 1 by 2, which equals ln n factorial plus n minus n plus 1 by, oh sorry, actually this is not n plus 1 by 2, this is n plus 1 by 2. So I was making this mistake all the way around. So n plus 1 by 2 times ln n. So now try to use the claim 1. So what is xn plus 1 minus xn? It's log of n plus 1 minus half ln 1 plus n plus 1 minus n plus 1 ln n plus 1 plus n ln n. So this is ln. So ln n plus 1 factorial minus ln n factorial equals ln n plus 1. So that's our first term. And the second term is n plus 1 minus n, that's 1. So this is the 1. And then n plus half times ln n. So n plus half times ln n minus n plus 3 by 2 times ln n plus 1.
So the very first term is ln n whole factorial or ln n factorial?
ln n plus, this one, ln factorial.
Yeah.
I mean, L of log of n factorial. Okay. It's like, if you expand this, it's log of n factorial. So this is n plus n of n. So it's n power n plus half by n plus 1 power n plus 3 by 2. Right. So dividing by n, we get 1 by n power n plus 3 by 2. So we have to divide by n plus 3 by n power n plus 3 by 2 inside log. So it's the numerator we get minus 1, right? Minus 1. Just a minute. So what is exactly the difference coming? Just a minute. So minus n plus 1. So the half times ln n plus 1 minus half times ln n, that gives us this second term. And the n ln n and n plus 1 ln n are copied here. Let's say this is the second term and this is the first term. Okay. Now it's so now simplifying further. This is so ln n plus 1 and n plus 1 ln n plus 1. So minus ln n plus 1. Then we have a minus ln 1 plus 1 by n. Then we have a plus n ln n and a plus 1. So taking minus n common from these two terms, it's ln n plus 1 minus ln n. So 1 plus 1 by n minus half times ln 1 plus 1 by n plus 1. So it's minus of n plus 1 by 2 times ln 1 plus 1 by n plus 1. So that is xn plus 1 minus xn. Okay. Uh, now this is ln 1 plus 1 by 1 plus 1 by n. And from claim 2 or claim 1, where was it? Yeah. From claim 2, we know ln 1 plus x minus x plus x squared by 2 is less than or equals to x cubed by 3. So from claim 2, ln 1 mod of ln 1 plus 1 by n, 1 by n minus x plus x squared by 2. So x cubed by 3. Now we have to multiply by n plus half minus n plus half on both sides to we'll anyways apply mod on both sides. So let me do away with the negative sign. So this thing mod of n plus half ln 1 plus 1 by n plus 1. This is equal to ln 1 plus 1 by n plus half ln 1 plus 1 by n plus 1. So less than or equals to n ln 1 plus 1 by n plus half ln 1 plus 1 by n plus 1. This is triangle inequality. Taking the n and half out, we get n plus 1 by 2. Just a minute. Okay. We have to supply the. Oh, sorry. Was this plus 1? Oh, damn. So I took the mod here, but then this plus 1. Sorry. This plus 1 changed to minus 1. Okay. So this plus is minus. This is minus 1. Minus 1 plus 2 by n. Let me not close the bracket. And this is half times 1 minus 1 by 2n minus 1 by 2n plus 1 by 4n squared minus 1 by 4n squared. So now we apply the triangle inequality to get n times, sorry, 2 by n squared plus half times n squared, and the minus 1 by 4n squared becomes, since we're taking an upper limit. So now from claim, from this result, not this result, this one, let me write it in the bracket, 1 by 3x cubed. So n times, or n times, not x, is n. So it's, sorry, so it's 7 by 12 n squared 6n cubed. So this was an upper bound for mod of xn plus 1 minus xn, right? I'm taking, oh yeah, we have to sum over, so summing over 1 through n and taking in limits.
So which statement was marked as star?
This one, the one we got from the
Okay, sir.
claim 2n. Yeah. And since we know 1 by n square and 1 by n cube converges, so this thing actually converge. This limit is less than infinity. Just a minute. So therefore, so this limit exists, and now from claim 3, I guess. This is claim 3. Oh, sorry, it was claim 1. Implies this limit exists. And what was xn? This limit exists, and therefore limit n tends to infinity e power xn. This limit exists. Now why is this true? Since fx equals to e power x is continuous over r. Uh, it's not only continuous, it's also differentiable. Okay, so not necessarily. So we just need the continuity property. So what does continuity imply? There is a sequence definition of continuity. I guess I mentioned it in the first class of calculus, that if we have a sequence xn which converges to some point a, then and we have a continuous function fx, then f of xn, the sequence f of xn converges to the point f of a, given f of a is well defined. So from that we have uh, this this limit exists. Okay, since the limit of the x's exist. And this implies limit n tends to infinity. Now we can remove the log n factorial by e power minus n times n plus 1. We may call it c is less than infinity. So claim 3 is proved. Now we'll find the value of the limit. Actually, we'll prove it's equal to 2 pi, square root of 2 pi. So that's our claim 4. Actually, we need to prove another claim before we try to find the limit. So okay, so since it involves exponential n power n plus 1, n plus half, right? So claim 4 is something different. So we define a sequence of integrals, integral 0 to pi by 2 sine power nx dx. The n is inside natural numbers with 0. So now since sine nx is inside minus 1 to, or mod of sine of nx is in between 0 and 1, which implies sine n plus 1x less than or equals to sine nx. which implies taking integrals. Is this mode necessary? Sin x and n plus 1x was negative, then n plus sin nx would have been less than that. Okay, we are anyways taking only positive values of x in this interval. We don't need that mod here, since x is positive. So integral 0 to pi by 2 n plus 1x, integral 0 to pi by 2 n plus nx. So in plus 1 is less than or equal to in. Right, and also, so this is one result. And in is so sin nx. So I guess you know the how we integrate by parts. So as a quick reminder, integral of u and v, actually both are function of x. So ux times vx dx is this is the first function. Ux is the first function, vx is the second function. So it's ux times integral vx dx minus integral of u dashed x times, not enough space, minus integral vx dx dx, still not enough space, vx dx dx. Okay, yeah. So actually the second function is 1. So sin nx, integral of so 0 to pi by 2, x is pi by 2. And this is integral n sin n minus 1x, and integral of dx is x. So this is now just a minute. Okay, so we have to apply by parts once more. So again apply by parts. Right. So this is sin n minus 1x integral. Sorry. This is not sin, this is cos. N sin n minus 1x times cos x So cos x sine n minus 1x times x dx. Just a minute. Okay, so I think this won't work. I can't take the second function as n plus 1 and find a suitable recursion for in. Sorry. So instead I will consider in as sine n minus 1x times cos x. Now this is our first function. So this is our first function and this is our second function. Now applying integration by parts. So n minus 1 sine n minus 2 cos x. Integral of cos x is minus sine x dx. Sorry, not minus, plus sine x dx. So integral of cos x dx is plus sine x dx. Wait a minute, what did I just do? I did write cos x here. Yeah, so this was sine x. Sorry. Plus minus cos x. This would have been sine. Integral of sine x is minus cos x. This is 0 to pi by 2. And cos pi by 2 is 0 and sine 0 is 0. So this is 0. Integral n minus 1 sine n minus 2x cos squared x dx. So now we can break it up as 1 minus sine squared x sine n minus 2 dx. So it's n minus 1 times sine n minus 2 minus plus sine squared, not sine squared, sine nx dx. So this is equal to in. The first term is in minus 2. The second term is in, right? Oh, sorry, I missed n minus 1. So minus in equals n minus 1 in minus 2. This implies in equals to 1 minus n by n in minus 2. Just a minute. This getting a negative sign move. It should be n minus 1. I messed up a negative sign somewhere. So n minus 1. Okay. This was minus. This was minus. This wasn't minus. And this is n minus 1. So this is our Wallace formula. Wallace. And one for cos x also exists, I guess. Oh, actually, in integral 0 to pi by 2 sine x dx equals to integral 0 to pi by 2 sine pi by 2 minus x dx equal to integral 0 to pi by 2 cos x dx. So this is same for cos x also. Okay. So using this recursive formula, we can find the integral in by breaking the recursion down. So uh, see, we can expand in plus 2n plus 1 as 2 by n 2n plus 1 times I 2n. Sorry, I 2n minus 1. So it's reducing by a factor of 2. So 2n plus 1 times it will be 2n minus 2 by 2n minus 1. Then it will be I 2n minus 3. And then it will go on till we get I1. So it will go up till, if we put n equals to 1, we get 2 by 3 and I1. So now what is I1? Sin x dx cos x. Pi by 2 is 0. 0 is 1. So it's 1. Sorry, I mean plus. Therefore, I2n plus 1 is so how can we write it compactly? So product over I runs from n through 1 to n minus I mean 0 through 1 to n minus I 0 through n 0 through n minus 1. So first one is 2n minus I plus 1. Last term is 2 by 3, right? Okay. So this is the formula for I2n plus 1. Similarly, just a minute. I2n is, sorry, so I0. So let's see what's I0. It's 1 time dx of pi by 2. Therefore, we have a formula for I2n as product of items from 0 through n minus 1. Uh, 2n minus I minus 1 by 2n minus I times, or I can just multiply by 2 here. So now we can try and find the limit of limit n tends to infinity I2n plus 1 by I2n. So what is this limit? Just a minute. It's not cancelling out. Okay, so we can use sandwich theorem. So we have proved. So at first we proved in plus 1 is less than or equals to in, right? So that is equivalent to in is less than or equal to in minus 1. And in minus 1 from this Wallace formula, it's n plus 1 by n times n plus 1, right? I'm reversing it, okay. So this implies n plus 1 by n is less than or equals to in plus 1 by in. Okay. I divide in plus 1 on both sides. Sorry, in. I mean, yeah. So that gives us, this thing is 1. Okay. We have to invert it. So this implies 1 less than or equal to n plus 1 n less than or equal to one is less than or equal to in minus 1 by in, and in minus 1 by n is equal to n plus 1 by n in plus 1 by in, which implies inverting it, in by in plus 1 times n by n plus 1, which implies n plus 1 by n is greater than or equals to in by in plus 1. And as a lower limit, so what is the lower limit? Yeah. So we also know it's less than in, which implies in by in plus 1 is greater than or equals to 1. So hence we have the 1 is the lower limit. Now taking limits both sides, on all sides actually. This is just 1. So this converges to 1. This is already 1. So by sandwich theorem, the limit in between also converges to 1, or it is 1. Okay, so why did we take so much pain in proving this limit equals to 1? Because now we will try to show, so the last claim 5, because actually our claim was limit n tends to infinity in plus okay, you can say it, equals 1, which we just a minute. Okay, like, does it matter? n plus 1 by n. So if a sequence converges to something, does it reciprocal also converge to that thing? Yeah, why did I get it wrong? So here we have 1 less than or equals to taking n, dividing by n minus 1, n plus 1 by n, we have n by n plus 1 is less than or equals to this thing. So this is less than or equals to and yeah, we can divide this by in instead. So in by in plus 1 is less than or equals to 1. The upper limit is 1, and now the limit becomes in plus 1 by in. Sorry. So it was in plus 1 by in. I guess it's reciprocal also tend to the same thing. Whatever. Never mind. So to correct this one also. Right, so now claim 5, the last claim. So the last claim is I to n plus 1 by I to n equals 1 by 2 pi times n tends to infinity n factorial by e power minus n power n plus 1 by 2 whole squared. Observe that if we can prove this, then we will suppose this limit is L, and we know this limit is 1. Okay. So observe that if claim 5 is proved, L equals to square root of root pi. Yes, L equals to square root of root pi. Right. And that will prove our Stirling's theorem. So now the proof. So now we know I to n plus 1 by I to n. I will just copy paste those expressions.
Sir, could you please show the statement of claim 5? Yeah, sir.
Oh, uh, so this is so 2n minus I. These things get squared up, and what happens to the denominators? Just a minute. So we can just write them out in longhand and check. So the numerator is something like 2n minus 2 by 2n minus 1, 2n minus 2 by 2n minus 1. Numerator is 2n minus 1 by 2n, 2n minus 3 by 2n minus 2, 2n minus 5 minus 5 by 2n minus 4. So this thing gets squared up, they get squared up, and minus 2 gets squared up, and this is left over. Okay, it happens to n minus 3. Yeah, so sorry, this is n minus 3. Right. Yeah. So they get squared up. So all of them are getting squared up, right? Yeah, sorry. So this is not n minus 2. So this is n minus 3. No, this is minus 2, n minus 4. This is n minus 3. Okay. So now they get squared up. This n minus 4 cancels. No, they also get squared up. Okay. So everything is getting squared up. Okay. So that implies n minus 2, n minus 1, minus 3. Okay. 2n, 2n minus 1, 2n minus 2, 2n minus 3. So thing is like 2n, then 2n minus 1, then 2n minus 2, then 2n minus 3, then 2n minus 4, then 2n minus 5, like this. These things get squared up, and the thing that is left over is 2 by pi times 2n plus 1. Okay. So this is equal to taking 2 common, we get 2 power n times n factorial. N factorial. N factorial. This is, sorry. Okay, so now in the denominator and numerator we can multiply by n factorial. Now this thing turns into a 2n factorial, I guess, yeah. and uh, how many terms? Yeah. So there are n terms, right? N terms in the numerator and n terms in the denominator. We also have a whole squared. Okay. We have to divide and multiply um, by 2n factorial. Sorry, not 2n factorial. By 2 power n to n factorial. Since all the even terms are missing, right? So it's 2 times each factor of n factorial. So it's 2 power n times n factorial. So actually it's 2 power n factorial whole 4 by 4 by sorry, not 4, it's 2n factorial whole squared times 2 by 2n plus 1. Okay, so now we have to show it to be limit of n. Sorry. So now we have to somehow introduce e here. So let gn be equal to e power minus n times n power n plus half. Okay. And we have already proved from claim 3, I guess. So from claim 3, limit n tends to infinity, n factorial by gn. This is some limit L less than infinity. So this converges. So now this thing. So instead of n factorial, okay, so limit n tends to infinity I 2n plus 1 by I 2n. Is this limit? I haven't given limit there. So now it's limit n tends to infinity times this thing. So we can divide by gn now. Okay. Inside the limit. Or so this thing implies limit n tends to infinity n factorial is Gn L. So we can replace n factorial by 2 power 4n times Gn whole power 4 by G2n squared. So above we have L power 4 and below we have L squared, so it's L squared, 2L squared times pi times 2n plus 1. Now expanding, so it's 2 e power minus 4n, n power 4n plus 2, n power 4n plus 2, is it 2? Oh, no, sorry. Yeah, n plus 4, n plus 2, sorry, it was half. Now, with the denominator, it's minus 4n power, 2n power, sorry, 2n power 2n plus 1. Just a minute, it's squared. Sorry, 2n, no, it's 4n plus 1. 4n plus 1 times c power 4n gets cancelled. So its limit n tends to infinity. 2 power 4n in numerator and 2 power 4n plus 1 in denominator. 2 power 4n will get cancelled. N power 4n plus, it's 2. 2 and n power 4n plus 1 L squared so we get limit n tends to infinity n, but this 2 gets cancelled, nl square pi 2n plus 1. Okay. So dividing by n, it's L square by pi times 2 plus 1 by n. Distributing the limits, it's 2 pi plus, this is limit n tends to infinity, L squared, so L is n factorial by e power minus n times n power n plus half whole squared. This goes to 0, so it's 2 pi times and hence we prove our last claim. And from this claim we know from the previous claim 4 that this limit is actually all 1. So 1. So 2 pi equals square root of 2 pi equals the Stirling formula. Right. So that's it for today. If anyone of you have any doubts, then please ask, or else I will stop the class here. So is it okay?
Yes, sir.
Okay. Okay then. Bye. Good night.
Good night, sir.